Right. I'd like to introduce you the second keynote lecturer, Professor Park from Columbia University. And her topic is structure and transport behaviors of liquid-like nanoparticle organic hybrid material designed for integrated CO2 capture conversion. Okay, Professor Park, are you ready?
Yes. Can you hear me well?
Yeah. Yes, please.
Okay, thank you very much, Professor Shaw. First of all, I'm very sorry that I'm not there with you guys to celebrate 60th anniversary of KICHE. What a wonderful event, and I'm sure you are having a great scientific and engineering discussions and celebrating all the remarkable advancements you have made last 60 years. So hopefully I'll be able to attend the KICHE meeting one day in person. I'm in New York City tonight. It's at 9:40 p.m., but this is the picture of New York City and Columbia University. So I'd like to bring you a little bit of New York to Korean meeting today. Do you see my next slide?
Yes.
If you don't see it, please let me know. So today I'd like to tell you a little bit about what we are working on to mitigate climate change and what to do to develop engineered solutions for climate change we are suffering today. And if you look at this, I can hopefully we don't need to talk about how carbon dioxide concentration in atmosphere is linked to climate change. But at the same time, this area, we've been working on how to capture or manage carbon dioxide from atmosphere for many years, in fact. In the United States, I think it was even before my time, so at least 3 decades, we've been working on this topic for a number of years. But about the 2013 and 2014, we started really doubting ourselves after even 20 years. Why don't we have carbon dioxide capture systems integrated into industrial systems and power plants? That was the time these 2 reports came out. We thought it was quite interesting because we were thinking that maybe decisions is a little too late. Maybe we should give up on these pathways. But at the same time, these reports actually said we need substantial multi-century climate change commitment created by past, present, and future emissions of carbon dioxide. This seems to be a very simple statement, but it's a huge statement because what we are saying is not only we are willing to or we are committed to go to zero emission technologies, but we are also committed to do negative emission technologies, going back into the history and picking up the CO2 we emitted decades ago. It's a very interesting, really strong statement. And since then, already almost 10 years passed, and a lot happened around the world, and especially in the United States. We had multiple presidents in the United States, and each president had a very different policy on or support for carbon management, research, and development. Our current president, Biden, had, as he started his presidency, had very interesting changes within the Department of Energy, which funds most of the carbon capture and conversion technologies in the United States. Within the Department of Energy, we have something called Office of Fossil Energy. And for the first time in decades, we actually changed the name of this office to Fossil Energy and Carbon Management. To me, I think it really reflects what we think we are going in the future. We still need fossil energy to bridge the gap of all the energy needs, but at the same time, we are really committed to defossilize and getting rid of and phasing out the fossil energy. At the same time, we are acknowledging the fact that managing carbon for future in both engineered and natural cycles is one of our key efforts we need to do within the Department of Energy. So not only they changed the name of the office, they actually started to have something called Energy EarthShot. And this Energy EarthShot is our US government's commitment showing that no matter what it takes, I guess we can debate about what no matter that part is, but no matter what it takes, we'll get there for the ultimate goal of net zero emission economy by 2050. In order to get there, there are a number of things we need to work on. And one of the things that they announced last June was the first one in hydrogen energy EarthShot. And this is the target of $1 per kilogram of hydrogen in 1 decade. This is really ambitious goal, in my opinion. And then more importantly, this clean hydrogen is very tied to what is its carbon intensity. So very carbon neutral or carbon negative hydrogen production within 1 decade with this price point, this would be really challenging, but it's really showing our commitment. And later last year, we actually had carbon negative energy EarthShot was announced. And this one is saying that we want $100 per ton of CO2 to achieve net zero emission by 2050. Again, this is including core aspects of carbon management, carbon capture, transportation, all the way to the storage or even utilization. So we really need fast advancement, even faster advancement in this area. And there's a lot of research going into this area at this time. So kind of looking at back what we have been doing last 30 years. We kind of knew already how to capture CO2 because we knew how to deal with sulfur. So based on all those technologies, we had liquid solvent, solid solvent, membrane, many different technologies we applied to capture CO2 effectively from especially coal-fired power plant, now natural gas-fired power plant. These are some of the good examples. If you look at the left-hand side, this is how we liquid solvents like monoethylamine or any amine-based liquid solvents would capture CO2. We capture CO2 at lower temperature, and we add energy by heating up the reactor to higher temperature to regenerate the liquid solvents. And ultimately, these liquid solvents have to last many hundreds and thousands and 10,000s of cycles for sure to be economical and also make sense for the life cycle analysis of the material system. If you look at the right-hand side, the largest scale demonstration in North America started in Canada first. But the United States, we really worked hard to catch up, and late 2016, we started our Petronova project in Houston. This is the picture I actually took. There are two columns, one for CO2 capture and solvent regeneration. We learned quite a bit by doing this scale up, but we still knew that this processing energy consumption for such a big liquid solvent system for CO2 capture would be very high. One of the reasons we always knew the processing energy consumption would be very high is because the concentration of amine, we can put it into these liquid solvents. Generally, these amine solvents can be used at maybe up to 30%, which means that you have 70 to 85% of liquid solvent is actually in fact water. And because water has a high capacity, heating up all the liquid solvent and cooling it down very fast and then doing repeatable cycles always require large energy consumption. Don't get me wrong, it does not mean we should not pursue this technology of amine-based liquid solvents. I think we further advanced this technology with a very interesting integrated heat and mass transfer. We can actually further improve this technology. But at the same time, the second generation of CO2 capture solvent, people start thinking about what if we have all these amine, but without having any water coming along the ride? So those are the materials I've been working on. So one of the great examples of water-lean or waterless CO2 capture solvent is, we call it NOMS, Nonoparticle Organic Hybrid Materials. This material was actually first developed by my friend Edwin Roger at Cornell University. And he came to me and said, Alissa, we made this really interesting material that behaves very similar to ionic liquid. Has almost zero vapor pressure, has an amazing chemical and physical tunability, but we don't know what to do with it in terms of CO2 capture. Can you take a look at it? And that's when we started to hypothesize that by tethering these polymers onto nanoparticle, as shown in this photo in the middle, that it still behaves like a liquid-like material. There's a lot of tunability. But also, because we are stretching and we are creating this free volume between polymer chains, we thought that we are using both enthalpy and entropy effect to really selectively absorbing these small gas molecules like the CO2 along the polymer chains. This was our hypothesis, and then we started testing this by looking at how to attach this CO2. And we actually found these materials that capture CO2 very effectively and very selectively. But one of the challenges that, as you saw the picture before, you actually have to have a large amount of these materials produced, not only synthesized and purified, and then put it into large reactors. So one of the first things you have to think about when you think about deploying these in the large-scale reactor is mass transfer. And that's kind of linked to viscosity. That's one of the first things you would take a look at. So if you look at these data sets, it's quite interesting that the bottom data set at the bottom right here, maybe you can see my mouse, that these are the amine-based liquid solvents. Very low viscosity, very easy to work with. You can either do triple spray power or triple bed reactor. There are many different reactor designs you can have. The second set in the middle is ion liquid. And the third set at the all the way to the top are our NONS materials, and others also verify this data. Not only they look quite apart from each other, but if you look at the y-axis, these are like the wall plot. So obviously our materials are like a sticky honey, with very high viscosity liquid solvent, and it's kind of understandable because it has very low vapor pressure. We kind of guessed that. So my colleagues like John Brannicky at UT Austin and working on ion liquid, they were very brave and said, well, we can tune maybe hydrogen bonding network and reduce the viscosity, and they did a really good job significantly reducing viscosity of ion liquid. So in my case, I was thinking about this, and I thought it would be much harder for us to, although we can tune the hydrogen bonding network and many other things to reduce the viscosity, we didn't think it would be worth it for us to work on that way. But one of the things we kind of went back was, why do we really care about high viscosity? Well, there are a few things. It would be really hard to move these liquid solvents around between the CO2 capture reactor and solvent regeneration reactor. But also, it would be very hard for us to create the interfaces between gas and liquid or CO2 capture. So that was about time my colleagues at Lawrence Livermore National Lab came to me and said, well, there are a lot of these high viscosity CO2 capture liquid solvent, but they're very interesting, but having these kind of issues. So why can't we develop other technologies? Maybe one of the methods can be encapsulation. It's as if you have very honey-like consistency liquid. We can chop them apart and kind of keep them apart. So we started thinking about this area, and the first generation we made was using microfluidic device. So the blue liquid is our NONS material, and the white liquid is the UV curable polymer. By creating the droplet inside droplet and then UV curing only the shell material and letting that to be gas permeable, we were able to produce materials like this. So it could be single core, a multi-core, and as we expected, all these materials start to capture CO2 much faster with kinetics. But we thought that, well, obviously multi-core works much better because there's more interfacial area. So why can't we push all the way, and as well as can we overcome not using microfluidic device, which is much harder to scale up? So second generation of encapsulated NONS liquid solvents, what we did was this material. We call this solvent impregnated polymer. Basically, instead of having microfluidic device, we directly add our highly viscous NONS solution into the UV curved polymer, and using high shear to make micro immersion of these two mixtures. And then we put these mixture of a microfluid, the micro immersion onto the flat surface, and then we can UV cure afterwards. By doing so, we were able to really make sub-micron droplets, or in some cases nano-droplets of these materials in highly permeable gas solid substrates. And it worked really well. And if you look at here, first picture shows the optical microscope of 10% all the way to 49% of NONS loading into our tegrod, which is a UV curable polymer. And once you cure the polymer, it looks like this. And if you look at the last column, it's showing the nitrogen mapping, which is kind of following where the NONS are. And obviously, nodes are well distributed in the system, and we were able to even order some magnitude improvement in this the CO2 capture using how fast we can capture CO2 using SIPs. So knowing this, we were super excited, and this is the data showing that 50-fold increase in CO2 capture kinetics. So what would you do after capture CO2? This was a big discussion. Until now, CO2 capture groups and CO2 conversion groups are kind of working separate from each other. But one of the important things we should do is that how to combine these into one system. And then about mid-2020, there was an interesting report by Mackenzie came out. And this was their estimation or prediction on what would happen by 2030, which is only 8 years from now. If you look at the light gray bubble, is their estimation on how much carbon storage will be doing. I really hope that they underestimated, because if you care about climate change, we need to do as much of the storage as possible. So hopefully this bubble will be even bigger than this. But at the same time, they had all these black bubbles, which is starting from fuel, construction, biochar, enhanced oil recovery, and plastics and chemicals. What they suggested was, before we get to the zero emission, we'll be starting with, at the same time in parallel, we'll be starting using CO2 as a feedstock for making chemicals, materials, and fuels, and so on. If you look at this picture of New York City, or even picture of the Seoul, or even looking around in your room right now, we use a lot of carbon. In fact, we do not like having elevated concentration of carbon dioxide in the atmosphere, but carbon itself is very important building block for everything we use. So in a sense that although we've been using the term decarbonization, full decarbonization of all the materials is not possible, because we need those. So in a sense, we need to do decarbonization at the same time defossilization of chemicals and materials. If we can still sustain our modern society using carbon, but as long as that carbon is non-fossil, that will be the path forward for the future. So let's imagine a new circular carbon economy. And if you look at the outside this blue bubble, perhaps we still have to use same chemicals and materials and fuels in foreseeable future. And maybe the way we consume these materials will be similar way. And some of these carbon, and many of these carbons will be left in environment or goes into the environmental system as a waste. But what if we create this new circular carbon economy and only input going into this will be renewable energy and hydrogen? Then we need to learn how to or develop carbon capture technology and conversion technology, which can be thermal, electrochemical, photocatalytic, biological, or even combinations of those. But we need to do this while thinking about tech to market, because we are not talking about niche area. We're talking about reshaping or redesigning the entire our commodity chemical market. And we need to learn how to do this better with economics and policy integrated into this. So this is a huge task. And I think our generation has tremendous opportunity, but at the same time a challenge of creating this. And one thing I'm not going to talk about too much is this hydrogen. The magic hydrogen, we usually think that somehow or other we're going to get split the water and get green hydrogen. But as I mentioned earlier in hydrogen energy EarthShot, this is not the easy one. So people talk about now many different colors of hydrogen: black, gray, blue, green, pink. I think the latest one I heard about is orange color. So we should choose the right color, which is with the least carbon intensity, and hopefully we can get there soon. So looking at every aspects of carbon cycle in the world, in the globe Earth system, we have to think about, in order for things to be circular, we need to find carbon, we need to harvest carbon, which is non-fossil. So as a chemical engineer, let's think about gas, liquid, solid, right? So gas will be air, liquid will be ocean, and solid will be rocks. And hopefully we don't need to tap into rocks, which is already well stored carbon, which means we need to harvest our carbon in future. In future, when we have a lot of renewable energy, directly from air or directly from ocean. You can also go through biological pathway of terrestrial or marine biomass. But today I'd like to tell you a little bit about direct air capture we've been working on at Columbia University. The challenge of direct air capture compared to point source captures are slightly different. This is the photo of Ironworks in Switzerland. It's one of the well-known direct air capture companies out there. They're really good at moving CO2 and they know how to do that very well. But they're still challenged by having the right materials to put in there to capture CO2 from 400 ppm, which is a big task. And because it's such a low concentration, we are not targeting 90-95% capture. It'd be more likely about 60% capture. And other challenges, which is different from point source capture, is we really need a low pressure drop, and it needs to be really stable under high oxygen concentration because it's under oxygen and air. And there will be fluctuating environmental conditions, some rainy days, some hot days, some dry days, and all those we have to deal with during our operations. So kind of going back to our nose material, I love the fact that our nose material has 0 vapor pressure. So we can leave a cup of nose outside and it won't evaporate for years and years and years. It would be fantastic. But the challenge is our nose materials are really highly viscous and also very sticky. So that it will collect all the dust outside. So what we envisioned was, I thought, well, we like encapsulation, but we want to minimize and control the pressure drop across the direct air capture system. So I started working with the Yongju at Cornell University and Michelle Kitter at Oak Ridge National Lab, and started putting these materials together between nose and PIM, which is highly porous polymer, which we can cure during the solvent evaporation. We electrospun into furnace filter-like systems, which with really low pressure drop. Another benefit was we selected PIN material because this material is hydrophobic. So that by doing so, during even rainy days, we can selectively capture CO2 while rejecting the water, which really improves the overall reaction processing energy consumption during the solvent regeneration. So here are some of the data. The data shows on the bottom left is the direct air capture systems, and bottom right is the CO2 capture system. Without going into a lot of details, basically we can control what polymer we actually use and what nodes we use, and also what is the polymer for the electrospinning we can use. And depending on what we are using, and we can even use the ceramic material, in some cases, really small polymers like TIPA will be left on the surface. And as you can see in the top figures, that some cases, the hydrophobicity will be disappearing. And in this case, we really like to keep the very hydrophobic surface at the same time having good CO2 capture kinetics. So let's go back to looking at the point source capture versus the direct air capture. One of the things about direct air capture, which is quite unique, is that what energy would you use to regenerate these materials? Because compared to power plant, where you do have a lot of waste heat lying around, direct air capture, maybe you don't have that. It could be middle of nowhere, near the injection sites. Then where would you get all this heat? So in fact, instead of heat, perhaps you have renewable energy, either wind or solar. Now the question becomes, how would you regenerate your materials using electricity, which is available instead of heat? So people start thinking about how to do non-thermal energy transfer. I think it's very interesting discussion we are having now, because by using non-thermal energy transfer, we can really achieve targeted heating. If we can imagine CO2 capture reactor and solvent regeneration reactor operates at exactly same temperature and only localized heating in the regeneration reactor, that will be the ultimately minimum energy input for carbon capture. So we developed this in SIPS material going back, but we incorporated magnetic nanoparticles, which is really good at absorbing microwave energy. And when we actually did the regeneration, as you can see on the right-hand side, instead of regenerating this material using steam for tens and half an hour or an hour, we were able to regenerate this material fully within a minute. And as you can see on the left-hand side, the amount of energy required to regenerate same amount of CO2 was significantly reduced, which is showing it could be very effective design of CO2 capture. So finally, I want to touch upon a little bit on how to combine CO2 capture and conversion. Looking back these materials, we start thinking that, well, once we capture CO2, if we have to convert to chemicals and fuels, what is the pathway we want to use? One of the pathways you can use is electrochemical reduction of carbon dioxide. There are a lot of research, especially in South Korea as well, looking into different catalyst development as well as reactor design and so on. So one of the areas I'm working on is electrolyte design. What we started thinking was, going back to our NOM study, these materials are quite unique and quite immiscible in water. So what if we use it as electrolyte additives? So that we can really increase the CO2 solubility in electrolyte, and then we can really deliver the CO2 to the surface of the catalyst most effectively. So this is the picture of two electrolyte systems. One is untethered polymer system, and then the left-hand side is NOM system. Only difference is the same polymer. One is tethered, the other one is not tethered. At the beginning, I really thought that the untethered system will have a better conductivity and lower viscosity. But we keep getting really interesting data in the lab. We keep getting that NOM-based electrolyte had a lower viscosity and higher conductivity. So we were getting really confused because if you look at the system, on the left-hand side, for the same concentration of polymers, we have a lot of nanoparticle, which is solid phase running around. So we were getting confused. So we went to the Argonne National Lab, did the USAX testing, and then we found out that there's quite a bit of signal coming out in the low Q range, suggesting that there's much different length scale materials that exist. In fact, much chunkier stuff. So looking at all these data, now this is what we think. The nose, this is bulk, very clear fluid, but then if you zoom in, there's agglomerates of these materials. And then if you even zoom in, it'll be tens to 100 nanometer aggregates. And all these impact on how CO2 is transported through these electrolytes. So we also looked at the SANS data, and then the SANS data also told us that depending on the secondary fluid, water for foam or product for aperic or aperic, these solvents make a huge difference in conformation of these polymers. And not only that, this tethered polymer, that's the one type of polymer exists in NOM-based electrolyte. We also have these polymers kind of stuck in between tethered polymer. Now we call them interacting polymers, and these impact significantly how these nodes interact with secondary fluid and then carry and transport the CO2, capture and transport the CO2. So once we put this CO2 in these various electrolytes, as you can see from orange data is regular electrolyte without just potassium hydroxide. And as we add more NOMs into the system, we have a hugely increased CO2 concentration in our electrolyte. There are two methods we hypothesized that not only these NOMs becomes internal reservoir of CO2, but also maybe act as a co-catalyst. So NOMs actually deliver CO2 to the surface of the catalyst and bend the CO2 just right so that their reactivity and reaction pathways may change. And in fact, we did see it. This is a typical potassium bicarbonate electrochemical reduction of CO2. And as you can see, as a functional potential, you have different amount of CO formation as well as hydrogen evolution reaction is suppressed at the increased potential. With the presence of NOMs, 10.8%, it changed hugely how much of the CO is formed versus the hydrogen. And if you look here, now with another system, with the one in the middle with the carbamate formation, the last one is just having Lewis acid base interaction between CO2 and NOMs. You can definitely see parasitic energy, the Faraday efficiency change because their reaction pathway is changing significantly. So we were really curious what happens at the electrolyte-electrode interface. So we went to NREL and tried to understand what happens when polymers get absorbed and deliver CO2 to the surface of the electrolyte and electrode interfaces. Without going into too much detail, this basically showing the modulus and deformation during actual electrochemical reaction. And when you have very short brush, as you apply the negative potential without any CO2 in this case, the polymer collapses onto the electrode. But if you have a case with the one CO2 in the system, in fact, there is a very different conformation and allowing much better transport between these polymer chains onto the surface of the electrode. And that's how all this transport and reaction, electrochemical reaction was changing. So I'd like to conclude that there's a lot to do for us to manage carbon and then creating a whole new way of making new chemicals or existing chemicals in a more sustainable way. And electrification really presents also good opportunities, but at the same time, very fundamental understanding has to be achieved by looking at the really fundamental research. And technologies, all the technology we should develop, considering our environment within the system boundary. Thank you very much for your attention. I would like to acknowledge my funding agencies and my students. Thank you.
Are there any questions or comments from the floor? Okay, Professor Park, thank you for nice presentation. I have a quick question.
Mm-hmm.
Yeah. Basically, your hybrid solvent is
Yes.
PEI-based solvent, right?
Yes.
So I was wondering about the regeneration stability and oxidation resistance and carbon to nitrogen ratio and other stuff.
Yeah, so our materials are, one of the reasons we like NOx is that its oxidative thermal stability is significantly enhanced compared to the starting material. So if you have a PEI, and a lot of the direct air capture materials is using PEI loaded onto or immobilized onto solid substrate. And many of the cases under high oxygen condition, even steam, it loses, it degrades like 80% over 100 cycles. That was our data. NOx almost no degradation. So I was wondering why, because it's a similar, same chemistry, and the only difference is that this short PEI, only 2,000 molecule away, is tethered onto the surface of the nanoparticle. So there's two hypotheses we have. Is the first that one of the end part is a cap on the surface, and then because of the charge on the surface, it's kind of stabilized. But I think it's one of the things. Second, more important thing is I think there's competition between CO2 diffusion through the nodes versus oxygen. CO2 diffuses a lot faster than oxygen in our system compared to PEI. So that by turning on the capture and release and capture and release at the right pace, we make sure that oxygen doesn't penetrate into nodes fast enough compared to CO2. And because of that, this material is very robust under high oxygen condition.
Okay, thank you. Please show me thanks to Professor Park again. Thank you.